So sometimes we don't know how good the process is, and process capability gives us just one number that tells us how good the process is. And if you are 6 sigma level or 1 sigma level, 3 sigma level, what kind of process you have that can be told by using this process capability. So how do we do that? How do we tell the level of process, how good this process is? That's the question that we ask, and process capability is the answer for that. Here's a process capability ratio that you can calculate. That's a CP, process capability ratio, equals upper specification minus lower specification divided by 6 times sigma. And this is capable process. A capable process must have a CP of at least 10. So if CP result in 1, then you can say, oh yeah, this is a capable process, pretty good process. You can say that. And if you have 1.33, then it's really a good process. And 6 sigma quality requires CP equals 2.0. So if you somehow achieved CP equals 2.0, that means it's a 6 sigma level. In other words, 3.4 errors per million product or services. So that's going to be a huge achievement for that business, 6 sigma quality they have. But if it is greater than 1, is capable, 1.33, very good process, reasonable process. But in many times, as I have seen so far, is that their process is lower than 1.0. So let's take an example here. Insurance claims process. Here's an insurance claims process, and process mean X double bar equals 210 minutes. In other words, it takes 210 minutes to process an insurance claim. About 4 hours, right? 3 hours and 3.5 hours long. And process standard deviation is 0.516 minutes. So there's a deviation of about half an hour. It does not make sense because it's 0.516 minutes. It's really quick. So I'm not sure if it is accurate, but anyway, this is just fictitious problem. Design specification is 210 plus minus 3 minutes. So their goal is to serve customers within 3 plus minus 3 minutes range. So 213 minutes or 207 minutes, that's their goal. And upper specification, lower specification is going to be now 210 plus 3 is 213. Minus lower specification is going to be 207, right? And divided by 6 times the sigma, 0.516, and you calculate that, then what happens is 1.938. So this is near 6 sigma, and I'll be really, really impressed if somebody does that. But I see a problem. Sigma is only 0.516. It's less than a minute, and I don't see it's doable. But anyway, it's just a fictitious problem. And if you have this low standard deviation, you will be able to achieve 6 sigma. So this process is very capable, near 6 sigma level. I'll be very much impressed by this. Now, CPK, process capability index, is minimum of these 2 values. The first one is upper specification minus X bar over 3 sigma. And the second one, on your right one, is X bar minus lower specification limit divided by 3 sigma. So we divide this specification in half and see if they are tilted or staying on the course and in the right middle of that. So that's what we see here. And CPK, if it is at least 1, is a very good and capable process. And a capable process is not necessarily in the center of the specification, but it falls within the specification limit at both extremes. And how do we calculate this CPK, process capability index? And if we see this example, new process mean is 0.250 inches, and process standard deviation is 0.005 inches. Upper specification is 0.251, lower one is 0.249. So let's first start with 251. 251 minus 3 times, the center line, the mean is 2.250, and divided by 3 times sigma 0.005. And then the second one, on your right one, is now 250 minus lower specification, so 0.250 minus 249 divided by 3 times the sigma. And you see which is lower. So CPK is the same, both of them, 0.001 divided by 0.0015 and 0.67. So this is below 1, and we can say that this is not capable process. So look at graphical interpretation of CPK. If CPK is negative number, that means it's the mean is the way over on your upper specification. So that's what it means. So if it is negative number, it's right here. If it is 0, then means your mean or your process mean is on the upper specification. If it is between 0 and 1, it's on the left side of your lower specification limit. And between center line and lower specification limit, your process is formed. That's what it means. If CPK is 1, it's exactly centered at the mean of the specification. If CPK is greater than 1, that means the range of your process is lower than the specification. So if I take an example, so you have a garage, right? And at your home, you have garage. So let me explain. So at your home, you have a garage and you have a car. Your car is your process, okay? And your garage is your specification. If your car is small and your garage is big, then there's no problem for you to fit your car into the garage door, right? So that's a good process. However, your garage door is small, specification is small. However, your car is huge, like what is it? F5 or F15, Ford F15, the kind of truck. And your garage door is very small. That means your process is not capable, yet your specification is very limited. As a result, you cannot make it into your garage door because the specification is small, but your process not good enough to fit into that garage door. That's how I compare CPK to garage door analogy. So then when to use CP and CPK? When the means is exactly in the center of their upper and lower specs, then they are the same. CP and CPK, there will be not much difference and you don't have to really use. However, when your mean is tilted to the left or to the right, then you need to use CPK and CP both to see whether the process is centered around the mean that you are aiming for. So that's the time you're going to use the CP and CPK. When the means is not in the center of the upper and lower specs, then you want to use CPK. And here is an example that we can take, the same example from Chevy Volt. And here we can calculate the upper limit and lower limit, and then sigma, and then we'll be able to find the CP and CPK. And in this case, upper specification and lower specification is the same, so there will not be any difference with that. So let me do this very quickly for you. So this is what we did. What I'm going to do is I'm going to just calculate sigma very quickly. So sigma equals STDV of all samples, and I want to find out. And sigma I found 15.02. So what do we have to do? Cp equals upper specification. For X bar is going to be upper specification is right here, minus lower specification, and divided by 6 times. So don't forget to use parentheses, otherwise your calculation will be messed up. And the sigma is right here. So we see the Cp is 0.5674. So it's not a capable process, we can tell. What about Cpk? And I said that's a minimum of upper control limit minus center line divided by 3 times sigma. And I need to use parentheses, otherwise I'll mess up with this calculation. Okay, so this is first one, and second one is minimum. So now this one minus that divided by parentheses 3 times sigma. So again, the same here, because I used the same specification that was derived from this table. But in reality, if you have a different upper control limit and lower control limit, for example, say your upper control limit is like 240 and your center line is 230, and your lower limit is 220, then it's going to be a completely different story. But in this case, it's only that. So what if I use this one? So let me do Cp equals upper control limit minus lower control limit divided by 6 times, and you have to use parentheses, 6 times sigma. So it goes below 0.22, so it's a really bad process in this case. So that's how you calculate that, and you can tell how good your process is right away.